Definition 12.48 First-time shrink. PROC satisfies first-time shrink if for any I1, I2 in the set I such that the size of Si to the j equals to m and the size of Si to the j plus 1 is less than m, such that Si1 to the j plus 1 intersect Si2 to the j plus 1 is empty. One CA PROC satisfies this since any player that shrinks his winning bundle is added to greedy J. Lemma 12.49. Given a C local approximation with respect to D that satisfies first-time shrink, the wrapper obtains an big O of log square of Vmax times C approximation for any profile of strategies in D. Proof: we continue to use the notation of claim 12.44, let P equals to the set of tuple Vi bar Si bar such that I lost and the size of Si to the j is less than m. Players in P appear with all their desired bundles, while players in R bar appear with only part of their desired bundles. However, ignoring the extra bundles in P incurs only a bounded loss. Claim 12.50. OPT of P is less than equals to J times OPT of R bar. Proof: define Pj to be all players in P that first shrank their bundle at iteration J by first time shrink, and since winning bundles only shrink, as I1 to the j intersect as I2 to the j equals to empty set for every I1, I2 in Pj. Therefore, OPT of R bar is greater than or equals to the summations of Vi bar summing for all index I in Pj. Every player I in Pj corresponds to a player in R bar, and all these players have disjoint bundles in R bar, since the bundles of I are contained in Si to the j. We also trivially have OPT of Pj less than or equals to the summations of Vi bar summing for all index I in Pj. Thus, for any j, OPT of Pj is less than or equals to OPT of R bar, and OPT of P is less than or equals to the summations of OPT of Pj summing for all index j, which is less than or equals to capital J times OPT of R bar. To prove the lemma, first notice that all true players are contained in P union R bar union W capital J. All retiring players belong to R bar union P. If a player shrank his bundle, then he belongs to P with all his true bundles, and if a player did not shrink his bundle at all, then he belongs to R bar with all his true bundles, and all non-retiring players belong to W capital J. From the above, we have OPT of P union R bar is less than or equals to OPT of P plus OPT of R bar, which is less than or equals to J times OPT of R bar plus OPT of R bar, which is less than or equals to 4 times J squared times C times the summations of Vi bar to the J, summing for all index I in Wj. Since Si to the j contain some desired bundle of player I, we have that OPT of Wj equals to the summations of Vi bar summing for all index I in Wj. Thus, we get that OPT of P union R bar union Wj is less than or equals to 5 times J squared times C wave times the summations of Vi bar to the j summing for all index I in Wj. Since j is less than or equals to 2 times log of Vmax plus 1, by lemma 12.38, the lemma follows. By all the above, we conclude the following. Theorem 12.51. The wrapper with one CA PROC is an algorithmic implementation of an big O of a log square of Vmax times C approximation for single-value players. This result has demonstrated that if we are less interested in reaching an equilibrium point, but rather in guaranteeing a good enough outcome, then alternative solution concepts that are no worse than classic dominant strategies can be of much help. However, the true power of relaxing dominant strategies to undominated strategies was not formally settled. Open question: does there exist a domain in which a computationally efficient algorithmic implementation achieves a better approximation than any computationally efficient dominant strategy implementation?